Good morning, everyone, and welcome once again to the Friday JKMRC seminar series. On behalf of the University of Queensland and the Sustainable Minerals Institute, we'd like to acknowledge the traditional owners and custodians of the land on which we meet today. It's a cold, rainy morning, and thank you all for joining. We pay our respect to the ancestors and their descendants who continue cultural and spiritual connections with country, and we recognize their valuable contribution to Australia and the global society. Today, it's my great pleasure to welcome Professor Courtney Young and Mitchell Harvey from Montana Technological University in the USA. Dr. Young is the Louis S. Prater Distinguished Professor in Mineral Processing and Extractive Metallurgy at Montana Tech. He's a graduate of 3 premier mining institutions where he learned mineral processing and extractive metallurgy. He loves to apply these separation technologies to recover critical metals and materials, as well as solve sustainability issues associated with waste processing, water remediation, tailings, slags, recycling, ash, dust, and spent pot liner treatment, energy reduction, and flow sheet development. While a faculty member for more than 32 years, Professor Courtney has taught numerous courses for students and short courses for professionals. His research has been funded by numerous entities ranging from industry to federal agencies. Dr. Young enjoys working with companies to help them solve problems and/or work on projects that cannot get to, particularly when he employs students, both graduates, and gets them real-world experiences. On the other hand, Mr. Mitchell Harvey obtained his bachelor's in chemical engineering in 2020 from Mississippi State University, where he became interested in mineral processing and extractive metallurgy. He pursued his MSc in metallurgical engineering / mineral processing engineering at Montana Tech, graduating in 2022 after doing a thesis on high pressure ablation, slurry ablation for improving separation of copper and molybdenum and flotation of gold tailings. He's now in his third year of PhD research in materials engineering and science at Montana Tech, doing a dissertation on selective oxidation for recycling samarium cobalt magnet, a type of rare earth magnet. It's been a dream, according to Mitchell, that he's doing his mineral processing PhD and also extractive metallurgy PhD. So with one accord, let's all welcome them. Today, they are going to talk about the history of critical minerals and application to recycling rare earth magnets. Thank you.
Eric, thank you very much. I appreciate that. And Belson, thank you for the invitation. It was a pleasure meeting you at IMPC in DC, so to speak. And if you remember, Mitchell was there as well. And so I'll just jump into this. I am hoping that I'm not speaking too much to the choir when I come up against this history of critical minerals portion of this talk. But at the same time, I thought I would throw in some information on Butte, Montana, because here's an opportunity to show you where we're at as a mining community ourselves. So if, let's see if I can get this to work. So that's what I look like, a little bit younger there, but I've lost a little bit of weight. So hello from a 10-pound lower weight guy. And of course, Mitchell and I are from Montana Tech. I would like to just start off right away with, I'm not going to read this one to you, but our research is conducted by the Army Research, or is funded by the Army Research Lab. And of course, whatever we say, they don't have to necessarily agree to or what have you. So these are our our discussions, etc. We do want to thank Joe Tripp Love, Ethan Mishler, and Heidi Steiger for their help in the lab. They would help clean up. They would help conduct some experiments, babysit for us if it's a long experiment going on. So what I've done is I'll be brief on the definitions and the history part, but I just want to have some fun with you guys, particularly for those who haven't really thought about along the lines of the history of critical minerals and materials. And one way of getting over the hill and making sure there's a constant supply of critical materials is by decreasing the risk, getting involved in recycling, etc. Some critical materials research have done a lot in this area. But in the area of rare earth elements, it's magnet recycling, and that's what you're going to hear about today. We'll eventually get involved in batteries. We're doing some work in coal. A lot of other people are involved in that area. And then we'll take resulting rare earth oxides and make metal using fused salt electrolysis. And because of the nature of Butte, Montana, copper being a critical mineral in the United States anyways, I've done some research on HPSA, and Mitchell actually did that work with his master's degree. And then done some work with Chevron Phillips Chemical Company. They have a depressant Orfom D8 for replacing the use of NaSH in copper moly separation. And then flotation when it comes to rare earths and copper together. We've obviously looked at frothers and collectors and doing some flotation modeling. And some of that work is involved my former PhD student, Rick Leducer. So rather than just doing this critical materials part here, the real outline is we're going to talk about Montana resources a little bit so you learn about Butte. And then Mitchell will take over with the samarium cobalt magnet recycling research that he's been doing. So that's the outline that you see there. And so critical, what does it mean? Of the greatest importance. And then when you define mineral, there's 5-6 categories that are very, very important for the definition of mineral. Number one, it needs to be naturally occurring, needs to be a solid, needs to have a chemical composition. It doesn't have to be precise all the time, but should be close enough to be in a particular composition, particular crystal structure. And because of structure property relationships, it'll have particular physical and chemical properties. And then, of course, another major part of the definition of minerals is that it is inorganic. You put the two of them together, and then a critical mineral means a mineral that is deemed essential to society, but its supply is at risk for a number of reasons. It could be national security or the economy or what have you, but predominantly the supply is coming from unfriendly countries. Disruptions can come in a number of forms, whether it's a government action, natural disasters, or increased demand in many other ways. Okay, the type of critical mineral varies with time, need, and country. So that's it for the definition part. Let's move on to the history. And let's jump back to the Stone Age, some 3.3 million years ago, when man was barely walking, wasn't even man back then. It was hominins and primates. And of course, what was important to them was sandstone and limestone. And eventually, we would use those materials to help us fashion flint and obsidian into blades so that we could have knives and axes and spears and arrows, and we could go hunting and things like that. But it wasn't until about, maybe 5,000 years ago that we started to come out of the Stone Age into what we call the Bronze Age. And of course, bronze is bronze because of the importance of tin, which we get from cassiterite, and the copper was coming from predominantly cuprite and chrysocolla, but some chalcopyrite. And somebody somehow figured out if you mix the two together, you get bronze. And sorry, I got a little ahead of myself. I'm forgetting to hit the return button. And then in 1200 BC, not but 3,000 years ago, the Bronze Age just collapsed. And within a 50-year period, it's not really well known how it collapsed from region to region. It's just that she was gone, and in came the Iron Age. And here, the critical materials are minerals are hematite and magnetite. And those, of course, were used to make steel, even though it's called the Iron Age. We have figured out how to adopt the bronze copper making process and apply it to steel. That, of course, required higher temperatures and pure forms of carbon, if you will. It was no longer really coal, but it was metallurgical grade coal, et cetera, et cetera. Eventually, iron replaced, or steel replaced bronze. And because of that, kingdoms grew, became empires. We were able to feed the soldiers, grow farms, and have cities with some sort of security. When you got happy soldiers, you got a happy government. So technically, though, man is still in the Iron Age. 3,000 years have passed before anything really major would happen. And then that was the first industrial revolution, most of it in Great Britain and the United States, but across the world. Okay. 1760 to 1830 was all about industrial mechanization. And then shortly thereafter, the second industrial revolution took place, and that was technological advancement. Today, we have the periodic table at our mercy, if you will. Everything on that periodic table could become critical. And it's interesting that the United States lists at least 50 on one particular list and another 19 on another list. And the combination of the two, I think there's like 63 critical minerals being listed. Among those are copper, cobalt, and nickel, which typically, if you've got, not necessarily, but if you've got a copper ore, you've got cobalt and nickel as well. Not always the case, though. And then, of course, rare elements are also critical, and many, many others. Those would include the 50 and the 19 that I was talking about. This is the Department of the Interior and the Department of Energy. So combining the two lists and taking out the commonalities, it's 53 in all. Now that's a little bit different than copper and tin from the Copper Age and just iron from the Iron Age. 53 today, okay? Aluminum, antimony, arsenic, barite, beryllium, bismuth, cesium. I'm not going to name them all. There's the whole list, and we've sent you the PDF of this presentation, and you can see those for yourself. You probably already know them anyways, being the Sustainability Materials Institute. But the ones we'll talk about today, predominantly copper and cobalt, because it's cobalt samarium being recycled. And then, of course, the rare earths that you see on this list and a whole number of other lists on there. It's particularly the samarium that got moved. Oh, well. That should be circling the samarium. Okay, so enough of the history, and we're going to talk about now decreasing the risk. So when we decrease the risk, there's several ways you can go about that. You can increase domestic mining and processing. President Trump, I think it was not even 2 weeks ago, signed a executive order to start increasing domestic mining. Okay. We can also do that by starting recycling programs, and that's the research that you're going to hear from Mitchell. And then, of course, maybe sometime 50 years from now or whenever, we're going to replace samarium cobalt with something else. So we're always developing replacement materials. Okay. It's important to understand that most critical minerals and materials are byproducts of processing primary mineral metal ores, and that's where this plot comes into play. The circle in the very center are your primary metals, and it's pretty obvious that if you've got copper, odds are that you're going to have selenium and tellurium as byproducts of that copper production. And a little bit further away, you might have cobalt in there, and even further away, maybe some indium and other things. So all those minerals are on the critical list. And so you got copper, like I just said, tellurium, cobalt, indium, those are on the critical materials list. If you've got gold, maybe you have copper present with this, maybe you have antimony, because that's on the list. If you've got lead, bismuth is on the list. So in other words, if you want bismuth, you got to mine lead, antimony. If you have zinc, perhaps you have indium with it and germanium, and gallium and tin. With platinum, maybe you have cobalt as well. And some of you might know about Stillwater mine here in Montana. It's about a 3.5–4 hour drive from here. They have a significant amount of cobalt and nickel there. Okay. And of course, they have copper as a byproduct as well. And palladium and rhodium. Thank you. I always forget my R's. And lastly, all of us, what's not listed on any of this is we don't have the workforce. We're going to increase this production. We have got to do the workforce part. And so if there's any way for the University of Queensland and Montana Tech to collaborate and what have you, we should open the door and start talking. Okay. Interestingly, a lot of the rare earth elements that you see, I just circled in red there. Look at the primary minerals. A lot of people, you have a huge iron ore body on the west coast of Australia. Maybe you got rare earths in those. I don't know. Beach sands, as we know, particularly the titanium industry, you got rare earths there. And tin, you can also have rare earths as well. The importance of the iron ore today is look at how much that we produce a year. And this is just 2022. And then we take a look at all the other commodities. And in comparison, the amount of copper that gets produced compared to the amount of iron and steel is incredible. Incredibly different. Okay, cobalt is there and rare earths there as a overall, and maybe a tenth of that, 10% of that is the samarium. This was 2 years ago, like I just said. Another view of it is the famous baby picture from, was it Jim, part of SME? And here's your copper production, and there's your rare earth production there in the other category. And once again, look at the iron ore, 18,317 pounds that one baby is going to utilize during his lifetime. That's incredible. So copper supply and demand, copper consumption over the last 25 years accounted for half of the copper ever mined. Copper consumption over the next 25 years will be equivalent to all of the copper mined to date. Australia and the United States are pretty good suppliers of that, but nobody matches Chile. Increasing demand requires increasing supply. Chinese copper production is actually expected to go down, and so that's going to end up being a critical material for them, if it's not already. China is compensating by taking over production elsewhere, in the Congo, in Peru, and what have you. So they are getting those sources. Supply could come from new discoveries. New discoveries, though, are pretty rare. Once you find one, though, they tend to be quite large. And major discoveries are rare. Getting them into production is the difficult part because of mining sustainability issues, and that's where we come in. Historically, you can take a look at this plot. China is in the purple, and that's what I said. They're not a huge producer, but eventually it's going to stagnate. Okay, Chile here in green is the dominant source, and they're going to be playing a major role. But take a look. It's 60 years from now, copper production, we're going to be out of ore. We got to find new sources or replacement materials. So just take a look at copper production throughout the world. Just want to mention Australia is a major player, but they're only 3% of world production. Take a look at Chile at 36% production. The United States, where are we right here? 11% production. So not too different, but between us, we're pretty solid. This is by mine. And if you take a look at the top mines in the world, Australia is number 26 on the list. I think that's Olympic Dam. I can't read that fine print, but I'm pretty sure that's correct. Okay. Again, major discoveries are rare. Look at the last one up there on the list of 1981. Okay. So we need to do better. Of course, copper production depends on whether it's a porphyry copper type ore or sediment hosted. And of course, that defines the type of process that you're going to use. Are you going to do flotation and then pyrometallurgy? Or are you going to, here's the pyrometallurgy route here. Or are you going to, and then what do you do with the concentrate if you're going to do flotation and then go into solvent extraction and leaching? You can go, of course, with the secondary sulfides and oxide production, go directly into leaching. Either way, you're going to end up with copper metal. Okay. So I want to take the time now just to walk you through a little bit of Butte, Montana before I turn this over. Most of you know that we have the Berkeley Pit. This is the city of got to walk you through here, show you the pictures. Here's Butte, Montana right here. Berkeley Pit right here. This is no longer operating. The operating mine is the Continental Pit that you see right here. Okay, and the tailings pond from this operation down here, this is the concentrator area, is the tailings is up here, and that's called the Yankee Doodle tailings. Okay, it's not a huge operation. It's 50,000 short tons per day. It's low grade. It's 0.3% copper, 0.05% moly. Sometimes I have to laugh at those numbers because Irian Jaya, Freeport-McMoRan's operation, that's their tailings, and we're doing enough here to make money with that. So a little bit more close-up view of the process. Obviously, dominating the picture are the thickeners here. And just quickly, this is their process for the bulk sulfide production. So it starts in the main crusher, goes into rod milling, then it goes into ball milling from there, and you can see the row of ball mills in this sequence, or rod mill here. I think for every rod mill, it feeds 2 ball mills. and the ball mills are twice as large as the rod mills. Bulk sulfide concentrate flotation deck here. Fairly big. We do not use the small flotation cells because these were built in 1955, and that's what we're still using. These are the old Gallagher 200 cubic foot square cells. Here's a little bit close-up view of one of them immediately below the viewing stand, viewing area. And of course, the parts that go into it. You got the belt driving the rotor down below. You can see the rotor on this guy right here, and the stator that goes at the bottom surrounding the rotor. Okay. 200 cubic foot or 200 diameter super thickeners. They were super at the time. I think these are actually small compared to some of them these days. And they were, the underflow goes into staged 400 horsepower centrifugal pumps. And that's what centrifugal pumps that these are. There's 3 of them staged. There's one here, and then one here. And then finally this goes up and over to land level. And then the flotation turns over into from the rougher flotation cells into the cleaner cells. So this is your final bulk sulfide concentrate. That then gets shipped over to the moly plant. And here you have much smaller cells. These are around 100 cubic foot. You've got the rougher, you can't see it, but it's up here. This is the first cleaner, second cleaner, and then third cleaner. And each stage in there has a little bit of a regrind circuit, which you can see in the flow sheet here. Okay. In fact, there's the regrind mill right there. And one of the thickeners, I'm not sure which thickener it is in that process. Okay. And then there's a better view of the thickener that you see right there. Okay. And then the flotation product from the moly plant goes into packaging, and these are a little over 2-ton moly bags. And that is the Montana Resources property. I'm going to turn it over to Mitchell for the samarium cobalt and remind you that the cobalt, we do not have cobalt in Butte, but a source of cobalt is byproduct of the copper industry. And of course, samarium is the rare earth industry. So Mitchell.
Okay, so I'm going to be talking about my specific work on a selective oxidation process for recycling samarium cobalt magnets as it relates to critical materials. So first, I'm just going to give some background, discuss the process as a whole, give you our preliminary results to date, and then some overall conclusions about the process. First, it's important why we care about samarium cobalt. I'm just going to give a brief history of permanent magnets. So for most of human history, the best permanent magnet that we had, the only one that we even knew about was lodestone, which is naturally magnetized magnetite. And other than making compasses, permanent magnets were kind of a novelty until we discovered electricity and then electromagnetism. And then we actually had a use for magnets. So in the early 1900s, we had KS steels and MK steels. These are tungsten cobalt steels. And they were developed, they weren't particularly great magnets, but they were the first kind of attempts at strong permanent magnets. And then in the 40s and late 30s to early 40s, we discovered platinum cobalt. As you might guess, platinum cobalt was very expensive and only saw limited use, but it was the best technology at the time. And it is unique among all the magnets pictured in this graph in that it's actually ductile. So you can actually shape platinum cobalt magnets into very intricate shapes. You can draw them into wires, whereas all the other magnets are very brittle. You have to, shaping them is a lot more difficult. After platinum cobalt, we got alnico magnets. Alnico is aluminum, nickel, cobalt, so hence alnico, and then as well as iron. And these are unique in that they have the highest operating temperature of any of the magnets. Some of the grades of alnico magnets work all the way up to dull red, which is very unique. Most of the other magnets stopped working well before then. So they're still used today for that reason in certain applications. After alnico, we got to ferrite, and this is what most people think of when they think of permanent magnets. It's the black, hard refrigerator magnet. These are very cheap to produce. They're just barium oxide or strontium oxide plus iron oxide. They're very corrosion resistant, so they can work in very harsh environments, but they're not very strong. So if we want better magnets, we have to use more exotic materials, and that's where samarium cobalt comes in. Samarium cobalt was the first generation of rare earth magnets to gain commercial success, and it was not orders of magnitude, but it was 2 to 3 times better than most of the magnet technology at the time, and it retained that status for multiple decades until we discovered neodymium iron boron. Neodymium iron boron were much stronger. They're cheaper to produce because the neodymium is cheaper than the samarium, or even though neodymium is more expensive than samarium, the cobalt is more expensive than the iron. So neodymium iron boron are both cheaper to produce and stronger. So if they're cheaper and stronger, why do we care about samarium cobalt? So samarium cobalt magnets, they're either based on the samarium cobalt 5 intermetallic, those are the first generation of magnets, or the 217 intermetallic, that's the second generation, and the stuff I'm focusing on because it's the more prevalent technology today. And why we care about samarium cobalt is because even though it's weaker than neodymium iron boron magnets at room temperature, it has a lower, it's called the reversible temperature coefficient. So all magnets lose, their magnetic field strength decreases with temperature. And depending on the material, they decrease more or less as a function of temperature. So samarium cobalt loses less magnetism with temperature. So above about 150 Celsius, samarium cobalt outperforms neodymium iron boron. And so it sees a lot of use in very specific high technology applications, such as radar receivers, certain motors and like control surface actuators and airplanes. And so it's still used in very critical applications, although as a function of cobalt consumption, it's a very small percentage of the overall cobalt market. Besides samarium cobalt magnets, cobalt's also used mostly to make cathodes and lithium batteries. It's also used to make cemented tungsten carbide. So if you ever heard of like tungsten carbide tooling, people think tungsten carbide tooling is just pure tungsten carbide, but actually it's a bunch of tiny tungsten carbide particles glued together by a cobalt metal binder. So that's another one big use of cobalt metal, but I'm getting off track here. In addition to working at better temperatures, samarium cobalt magnets have better corrosion resistance than neodymium iron boron. So most neodymium magnets that you see, they have either a nickel coating or a polymer coating. And so if they get abraded or chipped or anything, they're going to start to degrade. And I'm not going to say that samarium cobalt is going to withstand being submerged in concentrated sulfuric acid for days at a time, but it can withstand being splashed by water, just more rigorous conditions than neodymium iron boron. And unfortunately, it is brittle. Samarium cobalt 5 is less brittle than samarium 2 cobalt 17, but you can see in this magnet here, it's got a nice chip out of it. So you have to be very careful in handling them, which is just an unfortunate property of these intermetallics. Oh, another interesting property I forgot to mention is that the 217 magnets are cool. So if you add gadolinium to them, which is another critical material, that reversible temperature coefficient becomes almost 0. So you can have magnets that have a constant field strength over a fairly wide temperature range. And that's extra important. And like I said, the radar receivers, those are really important there because they operate at various temperatures and you need that magnetic field strength to be constant. Courtney almost dropped his coffee cup. So in addition to samarium and cobalt, the 217 magnets also contain appreciable quantities of iron, copper, and zirconium. You can see the different grades in the table below. So there's the standard grade and the high temperature grade. And so all these elements, with the exception of iron, are considered critical in some capacity by various agencies, depending on who you listen to. And so we want to look at recovering as many of these as possible. And to do that, we're going to use selective oxidation. So intuitively, we know different metals oxidize more easily than others. So we have a generic metal plus oxygen going to a generic metal oxide. Gold, for instance, is very noble. If we have a chunk of gold, we can heat it up in air to very high temperatures, even to its melting point. And then when it cools back down, it'll be just as shiny as when you started to heat it up. Other metals like iron, for instance, are fairly reactive in air. And so if you have an uncoated iron specimen in the right atmosphere, it'll oxidize quite rapidly. And then metals like sodium are extremely reactive and they'll react instantly. Now, part of this is kinetics. of the reactions, but the other part is thermodynamics. So this is the thermodynamic equation where you take the free energy of the reaction and you do some math with it. But what it allows you to do is it allows you to calculate the oxygen partial pressure in the atmosphere. So what pressure of oxygen in the atmosphere above or below which a metal will not oxidize. So if we take all of our reactions, all our possible reactions for the pure metals in the samarium cobalt magnets, we can use this thermodynamic data and use this equation, and we can calculate the oxygen partial pressure for each of these metals. And so then we can draw some arbitrary line. Let's just say we have this line, and we're going to control the PO2, the oxygen partial pressure, along this line, along this temperature range. Any metal above that line is not going to oxidize. It's going to stay as a pure metal, or it's going to stay as a metal because there is not enough oxygen in the atmosphere to thermodynamically oxidize those metals. And then any metal below that line is going to oxidize. There's enough oxygen to oxidize them. And the placement of this line, I just said we're going to place an arbitrary line on the graph, but the placement of this line is very important. So our goal with this project was to recover as high a grade of cobalt metal as possible. So hopefully, ideally, it could be used for not only creating new magnets, but also other applications such as cemented tungsten carbides or lithium batteries. Unfortunately, cobalt and iron are very similar. They're not quite as similar as cobalt and nickel, but they're harder to chemically separate. And if we're going to try to retain the cobalt as the metal, we want to oxidize the iron away. So we force the iron to the oxide phase. The zirconium and the samarium are going to oxidize very easily. So we're going to control our oxygen partial pressure such that we don't oxidize the cobalt or the copper, but oxidize the iron, zirconium, and samarium. And an important intermediate compound in this reaction is samarium ferrite. So in the previous slide, I assumed all the metals go to their oxide with no interaction between metals, but that's not actually the case. So if we go back to the graph, I'm assuming iron plus oxygen goes to iron monoxide. Unfortunately, iron monoxide decomposes on cooling to make iron metal and magnetite. So even if we can oxidize all the iron in the sample at a high temperature, when we cool it back down, a quarter of that iron is going to go back to iron metal. And we don't want that. We want to try to have as low of iron in the cobalt as possible. And so we're going to try to form samarium ferrite. So iron metal reacts with samarium oxide to form samarium, the stable species samarium ferrite. And this is stable in that PO2 range that I was showing between the cobalt line and the oxygen line. And there's enough samarium in standard grade magnets to sequester about up to half of the iron to samarium ferrite. So if we can sequester half of the iron to samarium ferrite, then the remaining iron monoxide, when it cools, only a quarter of that will decompose. So we can sequester 7/8 or about 88% of the iron in the oxide phase, greatly reducing the iron content of our cobalt. And in the bottom right, you can see some of the samarium ferrite. This is some synthetic stuff that I made just to practice my process on. It's a nice orange solid. And so going back to this graph, we can also see, unfortunately, copper is a more noble metal than cobalt. So if we want to oxidize, if we're going to try to get rid of the copper out of the cobalt, we're going to have to oxidize the cobalt too. And we don't want to do that. We're trying to retain the cobalt as a metal. So what do? Well, fortunately, copper has limited solubility in cobalt. If we look at the phase diagram, below about 500 C, there's almost no solubility of copper in cobalt. And so I'm skipping ahead a little bit and showing you a brief result that you can see when we do this selective oxidation process, when all the other stabilizing elements, all the samarium and the zirconium that help stabilize the cobalt or stabilize the copper in the alloy are removed by oxidizing them, you actually get these blebs and streaks of copper that precipitate in the oxidized magnets. And so we're hoping we can somehow leverage this to separate the copper and the cobalt. So this is the overall reaction that we're building to. We've got samarium, cobalt, iron, copper, and zirconium plus oxygen going to samarium ferrite, iron monoxide, cobalt, copper, and zirconia. Then the iron monoxide is going to decompose to iron metal and magnetite. You might notice a few things about some of these species. Cobalt and iron are both ferromagnetic, so they're very strongly magnetic. The magnetite is very magnetic, not quite as magnetic, but it is still quite magnetic. Samarium ferrite is weakly magnetic, and copper and zirconia are not magnetic to any appreciable extent. So if we can somehow oxidize these magnets and then grind them and liberate all these individual phases, we should be able to form magnetic separation. And so magnetic separation, and then using no chemicals other than oxygen, we can do a pretty good job of separating all the different components. And this is the process that we've developed. the flow sheet that we've developed for that. So first we take our scrap magnets, crush them to increase the surface area, perform our selective oxidation process, grind them to liberate them, leaving us with the mixture of cobalt metal, iron metal, copper metal, magnetite, samarium ferrite, and zirconium oxide. We then do our magnetic separation. Our strongly magnetic phases, our cobalt and our iron, are recovered as is. Our copper and zirconium oxides are our non-magnetic fraction. We then leach those with your acid of choice. In this case, I'm showing sulfuric acid. And then we can control the EH and the pH to not dissolve the copper, but dissolve the zirconium. And then our weakly magnetic fraction, the magnetite and the samarium ferrite, we then send forward to a selective reduction step. So samarium is very difficult to reduce, whereas iron is fairly easy to reduce. As Courtney was saying, we discovered the technology to reduce iron centuries ago. It's very easy to reduce. So if we throw carbon or hydrogen at the samarium ferrite and the magnetite, we will reduce the iron to iron metal while keeping the samarium as samarium oxide. And that's how we're going to separate the iron and the samarium there. So this is our flow sheet. And this whole flow sheet this whole selective oxidation process revolves around controlling the PO2 within a fairly narrow window, as you saw in the previous graphs. So if you look at our graph here, the scale on the left, I didn't highlight it before, but this is the base 10 logarithm of the oxygen partial pressure in atmospheres. And you can see it's negative tens of numbers, negative tens of atmospheres. So for example, the cobalt oxide line at 700 degrees Celsius has an equilibrium oxygen partial pressure of 10 to the negative 18 atmospheres. That's so incredibly low. You're never going to get this oxygen concentration by just diluting oxygen with argon or some other inert carrier gas. So how do we get there? Traditionally, you would use mixtures of oxidizing and reducing gases, such as carbon monoxide, carbon dioxide, or hydrogen and dihydrogen monoxide. And these work very well. And if we were ever to scale this process up to an industrial process, the hydrogen water route would probably be the way to go. But on a lab scale, we just don't want to work with these. We don't want to work with carbon monoxide. It's toxic and flammable. And then hydrogen is also very flammable. So what choices do we have left? Well, these lines that I've drawn are the equilibrium between cobalt metal and cobalt oxide. So what if we just mix together cobalt metal and cobalt oxide? They're going to react at high temperatures, and if there's any extra oxygen in the system above the equilibrium value, the cobalt metal is going to oxidize to cobalt oxide, and if there's too little oxygen in the system below the equilibrium value, the cobalt oxide will decompose to cobalt metal, releasing oxygen. And what we're doing is we're just going to place, I don't have a pointer, we're going to place the cobalt oxide mixture, then we're going to place our magnets on top of that. The oxygen will diffuse and transport through the atmosphere and selectively oxidize our magnets. And we're trying to do kinetic studies to try to figure out the best way to actually do this. But for right now, this is just our setup. And our results so far, you can see this. So this is a cross-section, a zoomed-in polished cross-section of one of our selectively oxidized magnets. In the top left, you have our selectively oxidized zone. So the dark spots are your oxide particles, and the light spots are your cobalt and iron metal particles. And then the bottom right, you have your unreacted samarium cobalt. If we do X-ray diffraction on this, X-ray diffraction helps us determine what crystal phases are present. We can see that we have cobalt metal, probably some iron and cobalt metal in solid solution, samarium ferrite, and the unreacted intermetallic. This is a pretty noisy scan. It's pretty hard to get a good scan on this with the copper tube, but we can see pretty confidently that we have both cobalt and samarium ferrite. So the overall reaction that we were showing before, we're pretty confident it's progressing as we predicted based on thermodynamics. And this is also backed up with some other literature results. We go to SEM now. So this is a much higher resolution SEM image of a magnet, a commercial magnet that has been fully selectively oxidized. We can see a lot of interesting things. So for one, so this is a backscattered electron image microscope. And what the important takeaway from that is the brighter the area of the image is, the higher an atomic number is. So the very bright areas are rich in samarium, and the very dark areas are very samarium poor. Hence, bright areas are samarium oxides, dark areas are cobalt metal. And we get a very interesting oxide microstructure. So at the edge, the oxide microstructure is very fine. And then as you progress toward the interior, it gets very, very coarse. And so part of the work we're trying to do is trying to optimize this microstructure, trying to get this very coarse oxide, because this is very difficult to separate. These oxide particles are maybe 1 to 10 microns, and these are 10 to 50 microns, depending on how you measure them. And another interesting feature of the selective oxidation is you get this core of metal. This magnet has been fully oxidized for multiple days. And this is a core of copper, cobalt, and iron metal that segregates in the middle of this magnet. So if you can very easily break off the outer shell of this and get access to this nice meaty metal core. Unfortunately, to date, liberating the samarium ferrite in the selectively oxidized magnets has proved quite difficult due to the ductility of that cobalt phase. So those oxide particles are very small, and the cobalt is the continuous phase. So the cobalt metal completely encapsulates all the oxide particles. Cobalt is a metal, metals are ductile, and we knew this going into it, but we're hoping that if we ground the metals enough, if we cold work them enough, they would become brittle and we would be able to liberate the two phases, but that's just not been the case. So we've had to resort to our backup plan, and that is melting the cobalt. If you heat the cobalt to its melting point, it's going to melt and coalesce into one bead, and then the oxides are going to float to the surface. You let it cool, and you can then break the two apart. Unfortunately, this is a lot more, I say a lot more energy intensive. It requires higher temperatures, and so it's probably more energy intensive than other low temperature physical separation steps, but it works so far, and this is the best we have to date. So on the bottom left, we have our oxidized magnets in a crucible in an induction caster, and then on the right, you have the cobalt metal and the oxide that we recovered from it. So now that we have the oxide recovered, we have that samarium ferrite, how are we going to separate the samarium and the iron? I talked about before how we're going to do selective reduction, but how exactly do we do that? This is the reaction that we believe is happening. So our samarium ferrite plus carbon goes to iron metal plus samarium oxide plus carbon monoxide. And to do this in the lab, we just mix the samarium ferrite and carbon powders, pelletize them, heat them up to 1400 C under argon, and then this is what we get. We use carbon powder, like I hinted at before. We use carbon powder because it's very accessible in the lab, but the thermodynamics are very favorable, and there's no reason that this shouldn't work with other reducing agents, such as like water gas or just pure hydrogen. But the resulting product is blebs of iron dispersed in a porous samarium oxide matrix. And unlike the oxidized magnets, the continuous phase here is brittle. It's the brittle samarium oxide. So it's very easy to grind. And then iron, again, is magnetic. Samarium oxide is not magnetic, or it's at least paramagnetic. And so we can very easily grind and do magnetic separation to get a concentrate that is free of any iron. And you can see that here. This is X-ray diffraction again. Each of these peaks are labeled with what phase they represent. So this top line is the as reduced sample. We've got peaks for both the samarium oxide and iron metal. And then our concentrate that we've done by grinding magnetic separation, there is no iron peak. This main iron peak is completely absent in the samarium concentrate. And then the iron concentrate, we still have a fair amount of samarium oxide. However, this was a proof of concept test done in a mortar and pestle. We have plans to do this with much better grinding equipment where we think we can get full liberation of the samarium oxide and the iron metal. So this is all of our work to date. We've demonstrated that both samarium and iron can be selectively oxidized in commercial samarium cobalt magnets. Physical separation of the phases is complicated by the really fine microstructure, but the melt coalescence seems to be a valid method if nothing else works. Separation of the cobalt and the copper metal remains an issue. We haven't done much work into figuring that out. And the fate of the zirconium oxide is unknown. Because it only makes up about 2% of the magnets, we haven't stumbled across it when we're doing SEM EDS. We haven't actually found a particle yet. So we have yet to do a more time-intensive scan to actually find it. So we want to do some more tests and try to figure out where exactly the zirconium oxide goes and how we can recover it. Also, samarium ferrite, we can reduce it to samarium oxide and iron metal, just as we predicted. So I think Courtney's now going to finish up with some final thoughts.
All right. Nice job, Mitchell. So some final thoughts. We're now engaged, in my opinion, a third industrial revolution. So my question to you is the Iron Age over? Are we in what I would call a materials age, because we have so many more critical materials these days? And maybe some might even call it the space age. None of this happens without geology, mining, mineral processing, extractive metallurgy. These disciplines are the pillars of society, and you're starting to see a huge turnaround in the U.S. economy because our president, even though he can rub people the wrong way, I do believe he's going in the right direction. The easy ores are gone. Next gen engineers, scientists are going to need to find, extract, process, separate, and that includes domestic resources, primary and secondary materials. So my question to you is really that simple. I believe we're now in the materials age. We all need to get involved. Even that part is critical, that workforce. I keep forgetting to hit the return button. I apologize for that. But we can also, for new places, deeper underground mines, seafloor beds, undersea mines, nearby celestial bodies. We got a long ways to go, and we got a lot of places to go. Just some quick pictures. I think everybody knows what that is, but would you believe that that is from 20,000 years ago? And it's a mortar and pestle. And these are little cavities in a cave from 10,000 years ago. Both of these are from Israel, and they were used to grow beer or brew beer, believe it or not. And if you compare to a mortar and pestle today, sure. And of course, I had to grab a picture from one of my favorite beers or bars in Brisbane, the Catchment. Well, at least some things haven't changed. So with that, I'll be happy to answer any questions. I do want to thank Montana Tech for this opportunity. Queensland, University of Queensland Sustainable Materials Institute, and the people who funded this was the DevCom Army Research Lab here in the United States. And just to give you a little feel more for me, I'm a Green Bay Packers fan. That may not mean nothing to you because football's a little different there. But that's my wife and my two girls. Love the heck out of them. So go Pack, go. And sometimes in the later in life or later in the year, I grow a beard and I become Santa Claus. So I didn't have that picture here, but this is a picture of Butte looking down at the Montana Tech campus. So thank you again for the opportunity, and happy to answer any questions. And you can answer, you can only ask Mitchell, not me. I'm just kidding. I'm just kidding.
Thanks, Courtney and Mitchell. That was very insightful. Do we have any questions in the room? We'll go online.
There's somebody, I think I would give them permission to talk on this.
Nothing online.
There's one in the room.
Hi, how you going? My name's Andrew White. I'm a comms person, not a geologist, so apologies if this is a silly question. In terms of the driving force behind wanting to recycle these magnets, is it because of the demand, or is it because there are diminishing sources, or is it a combination of those two?
I'm going to let Mitchell answer that one.
It's just because that there's like the cobalt is a critical material, and so there's diminishing sources. So we're trying to recycle as much as we can, keep as much in circulation. Does that answer?
Thanks.
And by the way, there's no such thing as a dumb question except for the unasked one. So
There are about 2 questions online, and I believe you can see them. So if you can please answer those ones as well.
We're not seeing anything. You can see our chat.
Go back up to the. I was about to one thing you can't see. It's that.
Oh, wrong place. There we are. Okay. With the magnet recycling, have you considered grinding it first and then oxidizing it to give more oxygen exposure to the magnet particles.
Yes, that is the plan for like scale up, but what we're trying to do now is do a kinetic study to see how the size of the magnet beforehand impacts the final microstructure. Because if you saw that initial oxidation zone towards the surface, the oxide structure was very fine. And so we want the oxides to be as coarse as possible. But yes, we would probably grind it to a very fine powder if we were actually going to do this on a scaled up scale.
And Ian's asking, are there any moves within the United States to increase numbers of metallurgy students? And the answer is yes. It's actually a pretty tough game. I'm one of the 14 mining schools left. Montana Tech is. Actually, some people call it 13. And of those 13, 6 or 7 of them have metallurgy programs. And of those metallurgy programs, 2 of them remain only metallurgy, and they're metallurgical materials engineering. So it is rather difficult, but I do predict that there's going to be more metallurgy programs that do extractive metallurgy. They will probably retain metallurgical materials engineering, but I can see that they would develop their own extractive metallurgy programs, which would include mineral processing. Nikki, good to see you too.
Okay, in the absence of any more questions, why don't you join me again, thank Courtney and Mitchell for their presentation today.
Thank you for inviting us. It's greatly appreciated. I'm sorry we can't be there live because I'd love to go to that bar and have a beer right about now.
Thanks. Just a quick one. Next week, we'll have Dr. John Caulfield from QUT. He's going to talk to us about zircon zoning and implications for all fertility indices. And we'd love to see you guys again. Thanks, and see you next week.